happening here. As you know, I'm recording these, I'm screencasting, I'm posting to YouTube, and I did something like that a while ago, a couple years ago when I last taught this class, and I was looking back and I was shocked to see how many people had looked at some of my lectures, how many people had actually viewed them. I mean, it was a little bit gratifying, but I was going through and looking at the different topics. And then one topic that was the most popular, ironically, was hidden Markov models, which I know very little about and was not the topic of the course. So it was very odd to me that apparently over 5,000 people have watched my lecture on hidden Markov models when that's what I know the least about of everything that I lectured that term. They're brand new lecture notes.
Yeah, there's a good chance of half of this.
Oh, okay.
No, I don't think I have actually watched it.
Waited to hit the record button until after you said that.
Yeah. But anyways, let's pick it up. I'm really actually excited to go over the example that's coming up with optimal tracking. So we covered this last time, but I just want to do a little bit of a refresher. With optimal tracking, there's two different forms. There's one set of recursions for tracking what was called the joint posterior, but the joint posterior is a difficult thing to handle because it grows in dimension over time, and it's just, the recursions are simple, but it's only of theoretical interest because it's such a complicated high-dimensional object that it's just difficult to handle practically. The other type of recursions were recursions for the posterior of the marginal, which is what most of the tracking algorithms are really trying to estimate or track, including the Kalman filter, the incentive Kalman filter, to some extent particle filters. And optimally, Fu, do you mind shutting the door for us? Thank you. Optimally, this comes down to just being one integral that is kind of a prediction step, where you're essentially taking your previous posterior distribution, multiplying it by your prior, and then integrating over what the state was at time n-1. And that gives you not quite your posterior, but rather your sort of predicted posterior, where this is the probability of the state taken on various values, given all the measurements, but only up to time n-1. And then you do a filter step or a measurement update step. This has a number of different names. I use the word filter update here. And you multiply it essentially by your likelihood, which takes into account your measurement at time n, and then there's this normalizing constant that we're not really going to care about that gives us finally the marginal posterior that we're really interested in. So last time we went through the math and we arrived at this as our set of equations for doing optimal tracking. And then one of the things that's often overlooked in the textbooks and is overlooked in a lot of the papers that I'm asking you to read is the fact that you can actually do numerical integration of this integral, at least in low-dimensional problems of dimensions 1, maybe 2, and apply this. And a lot of the examples, including that example in CAPE and many of the other articles, are actually one-dimensional tracking problems where you've got a single-dimensional measurement and a single-dimensional state. And in those cases, you can do this numerical integration and get essentially the true posterior exactly, where the only limitation is how much computation you throw at it and how you represent this integral. So that's kind of a summary of where we left off. And then I briefly mentioned that with integration, there's a number of ways of doing it. We saw in Scott's homework presentation, use the triangular or the trapezoidal rule. There's also the rectangular rule, which is related to, I think it's pronounced Riemann sums that you learned about when you were learning calculus. So we can do numerical integration in low dimensions pretty easily, especially with the computational power we've got available at our fingertips today. This is a new slide that I added today, so those of you with printed slides may not have a copy of this, but one of the things that I need to point out that wasn't clear in my earlier draft of the slides is that the way we're representing the posterior is essentially by the heights of the different bends. And this, I should have recreated this plot because this actually isn't a PDF. The area doesn't integrate to 1. So think of it conceptually. I should have used a PDF where if you added the area of all the bars that it did add to 1, that would have been better. But the way we're representing the posterior when you're doing this type of optimal tracking is essentially by the bend heights. So if you've got 500 bins, then you're representing the posterior by 500 numbers. And remember, the posterior changes over time. And so at a particular time, your representation of the posterior is by those 500 numbers, if you have 500 bins, or sometimes these are called regions instead of bins. And that's something that you get to pick. When you're doing the numerical integration, you can pick the number of regions. At some point, you'll find that you hit a point of diminishing returns, kind of like what Eric was referring to earlier, and it doesn't help. You're just spending more computation as you add more and more regions. But you need enough that you can represent all the shape, all the fluctuations in the PDF. So you could almost think it's a little bit like Nyquist, but you would want to oversample by maybe a factor of 10. You know, is one way, I guess, of thinking about it. This particular graphical example, if this were a PDF, would be way undersampled. You'd want to increase it by like a factor of 10. Okay, so when you're thinking about optimal tracking, one of the things that wasn't clear when I've taught this before, at least initially until students studied the code, is that your representation of the posterior is with the heights of these bins. So however many bins you have those many numbers, and that's what represents your posterior at a particular time step. It's okay? All right. So this is the integral that we need to evaluate. And again, if our state has a single dimension in it, then this becomes a one-dimensional integral. And we know what the prior is because we have it from our process model, and we know what the prior or the previous posterior was because we have that from the previous time step. And you have to initialize it, but you initialize it with knowing what your prior is at time 0, and essentially just go from there. So we can go through and we can do the numerical integration with your favorite technique. One of the things that may not be clear is if you're going to evaluate this integral over a single dimension, the number of operations that's involved is the number of regions squared. And the reason for that is that to evaluate this integral, you've got to evaluate this at every single bin location. Right? You know, I mean, you're going to evaluate this, and you've got to have this for every single bin location. What each bin location, you're evaluating this integral from x bin to x max, and this ends up being a sum that has nr terms in it. So for every bin, you're evaluating an integral that, or really a sum. You're approximating an integral with a sum that has nr terms in it. And so when you implement that, that ends up being nr squared terms. So you don't want to go crazy with the number of bins you have. You say, oh, you know, computation's free, computers are fast, make it 1,000,000 bins, I don't care. Well, don't do that, because operations are going to be 1,000,000 squared, and even with fast computers, that's not going to work, even today in 2016. And I'll just mention in passing, very closely related to this. It's not quite the same, but there's a number of mentions in the papers that I'm providing that go along with this class where they describe these as approximate grid-based methods. The difference is that they're really talking about representing the PDF as though you're just sampling the center of the bin. And I'm more generally describing this as though you could do the integration in a number of ways. If you're using the trapezoidal rule, then you're technically using the edges of the bins rather than just the center. So it's very closely related, very similar idea, but it's a little bit different when they talk about these approximate grid-based methods, but it's a subtle difference. It's essentially the same idea. It's okay? Andy?
So because we're doing a numerical integration, then we have to limit our integration, right, to be a definite integral.
Correct.
Right? Which means that, does this mean we can't do this with priors or fat tails?
Well, it's just going to be more computation.
Okay.
You could, but now you've got a much bigger range, so you're going to have to throw a lot more cycles at it. But you can still do it. Any other questions so far? Is this
You still have to approximate the priors being finite, though.
correct?
Well, you could have non-uniform bin size. And reduce
Yeah.
computation time for the fat tail.
It turns out that there are entire courses about how to do numerical integration, and there's lots of different ways of doing it. And you're absolutely right. There are techniques that essentially use adaptive bin sizes and use big bins in certain regions and narrow bins in other regions, depending on how variable the function is. So you can go pretty deep in terms of how to do the numerical integration. But for our purposes, this is essentially going to serve as a benchmark for understanding how the other tracking algorithms work, and to convey some critical ideas about tracking that are often overlooked in the textbooks and in the literature. Let me move on. All right, so finally, I'm so excited to show you this example because it conveys a lot of different really good ideas. And again, this example that we're going through, basically what I'm asking you to do for homework 2 is 2 more examples that are very similar to the example that we're going through here. So finally, we have time. In homework 1, and when we were talking about estimation theory, we were lacking time. But now finally you can do time. So foo, you can estimate frequency if you want to, and see exactly what what the frequency is of those waves and how it changes over time. You could do frequency tracking as an example. This is actually closely related. This is obviously the measurement model. You can see y of n here. I'm representing it as a random variable. It's a scalar. The state is also a scalar, and you can see that the state can be interpreted as the angle of a cosine. And I'm multiplying it by 2 pi, so, well, you know how to do the scaling. This isn't really xn isn't in units of radians or degrees, but I think you know how to interpret it, especially if you've done a lot of work with MATLAB, where it likes to normalize things from 0 to 1. And then v of n, in this case I have additive noise again, that's the easiest case. And by the way, I saw there were some questions on the homework and maybe a little bit of confusion about how to go from a measurement model like this to knowing what the likelihood function is. And I did an example when we were talking about estimation, but I should probably say a little bit more about that. Usually, in most applications, you have measurement noise that has 0 mean. That's almost always the case. And when we're looking at the likelihood function, this technically is a likelihood function when we fix yn and we think of this as a function of x of n. But when you're solving for the likelihood function, it's better to think of this as a conditional probability, where you're thinking about what is the PDF of y conditioned on knowing what xn is, on knowing what the state is at time n. And if you know what the state is at time n, then this whole term right here just becomes a constant added to a random variable with a distribution that's known, and usually that has 0 mean. And so the PDF of y, generally speaking, when you've got one random variable is equal to some constant, I'm going to call it mu, plus another random variable, v, where again, this one is random. I'm going to kind of try to make that boldface, and this, of course, has to be random, but this is constant. When you have that, the PDF of y is going to be equal to the PDF of v, but it will have a different mean that's shifted by whatever this mu is. And we have exactly that case here. Whenever you have additive measurement noise, and you're conditioning it on knowing what the state is, if you know what the state is, no matter how nasty this nonlinear function is, this is essentially just a constant because it's given. It's conditional probability conditioned on knowing what x of n is. So you treat it as a constant, which means PDF of y is equal to the PDF of v, but with a different mean given by whatever that nonlinear function is, evaluated at the known value of the state. So hopefully that helps a little bit in knowing how to solve it. It's more complicated when you don't have additive measurement noise, and then you have to do more math, and you may end up convolving PDFs and doing other complicated things. But in many applications, it's a pretty good model to model the effects of the process or the measurement noise is an additive effect. And often you can lump them together and wave the central limit theorem flag, and that's why it's often justified, at least in your measurement model or your observation model, to model this as a normally distributed random variable. And then the only question is, well, what's a reasonable variance? And usually you can figure out a good estimate of that variance. If you can take measurements while holding the state constant, then you can usually characterize your sensors and get a good idea of what that variance is. So hopefully that helps a little bit with what came up during the homework. And by the way, I'm sorry, I'm not a D2L expert. I tried to configure it so it would notify me whenever there's a post on the discussion forum, but it's not working. It seems to be configured that way, but I never get the notices, so I have to check. That's why it's a little bit slow to respond. Okay, So in this case, let's look at the likelihood function. Again, based on what I just described, it's going to be a normal distribution with a mean given by the cosine of 2 pi xn. So it's quite straightforward. But the really cool thing, I kept mentioning this coming, and the really cool thing is it doesn't look anything like a PDF. I think in all the examples, including what we saw from Scott and Fu in their homework examples, so far every likelihood function you've seen looks like a PDF. But here's an example of a likelihood function that looks nothing like a PDF. It doesn't have unit area, and in fact, it doesn't even have finite area, and it doesn't have to. There's nothing about it that would say that it should. You don't look like you like that, Andy.
That's good. It's just, I was trying to think of other examples that I ran into that was like that.
Yeah. So this is the plot of the likelihood function. Again, we're plotting it as a function of x. If I plotted this as a probability, where x took some fixed value, and then I plotted p of y, that of course would have unit area. That would be a probability. But when we plot this as a function of x, then it's a likelihood function. It doesn't have to have unit area. It doesn't have to have a PDF. Usually isn't, and usually doesn't. And if we consider a single observation, I had to pick an observation to generate this plot, and I just chose a value of 0.2. I could have chosen anything I wanted, but I chose 0.2. And of course, if you were doing maximum likelihood estimation, you would be like, oh, shoot, I've got an infinite number of maxima that are of the same height. There's not a unique maximum to this likelihood. So if you're doing maximum likelihood estimation, you'd kind of be stuck. And that shouldn't be surprising. I mean, being a cosine, if you're taking a cosine of something and you're trying to estimate what you're taking a cosine of course there are many equivalent angles that would generate exactly the same output for that cosine. We do have this noise as well, and that has a bit of an effect, but nonetheless, when we're doing maximum likelihood estimation and we say y naught is equal to 0.2, there are many equally probable values at x of n, or equally likely, I should say, values that xn could have taken on. So let's go Bayesian, and let's say we happen to have prior knowledge that at least at time 0 that it's a normal distribution with some variance. And we're not going to have a problem of multiplying two normals and having it be normal as Scott had encountered, because this likelihood is clearly not a normal. So let's see what that looks like. And we end up with this kind of neat thing, which I think nicely kind of shows the Bayesian framework, illustrates it yet again. We saw a nice example when we were talking about estimation theory, and here's another one where, again, I'm evaluating this just at one point in time and for a prior distribution on x at a particular time. And the prior now is shown by the green line. It's just a Gaussian. And when I multiply the Gaussian by the likelihood, you end up with a posterior, or at least something that's proportional to the posterior. It looks like I normalized it so it does have unit area, shown by the red line. So kind of neat, right? That's the posterior. It's multimodal. In preparation for the final quiz, or even on your project presentations, where I may ask the question, which measure of central tendency would you use? If you now, based on this posterior, have to give me an estimate of what you think x is. If you didn't know, but you had to tell me what x is, what would you guess? You would probably pick either the mode, the maximum, but the maximum isn't unique, even for the posterior, or maybe the median or the mean. And I'll make this rhetorical. This is just a reminder that it depends on your application. It depends on what you're trying to do. And you really need an application context to justify whatever the choice is of what you're going to be, which of these things you're going to use to estimate what the state is.
I feel like if your posterior is symmetrical, though, it just seems to make sense to use the median or the mean. Like, I don't know why, but
Aren't they all the same
Well,
if it's symmetric?
This is a nice case.
Not the mode, but
where the mode isn't. The mode's a different place. And if I had formulated this a little bit differently, I would need to adjust the variance of one of the terms. I could have made this go much deeper, so that
yeah, right.
so that it's very improbable And in some applications, you'd be like, if you're playing the lottery, you don't want to do that.
Yeah, right. Okay, fair enough.
Okay. So finally, got a single dimensional state space model. Now we're going to do the integration that we talked about, and I'm going to take a very closely related. This isn't quite the same. This is a little bit different because it's a sine, and I didn't do 2 pi. I did 2 pi over 3. So this is multiplied by an angle x of n. So it's very closely related to the measurement model we saw in example 1. But it's different a little bit just because it's a sine and this argument is slightly different. But otherwise, it's the same. And now I've got a process model. And this is probably the most common process model that you're going to see. It's it's related to the process model, for those of you that took 539 last fall, that you used when you were trying to use this as a type of adaptive filter. This is an autoregressive process where it basically says the state at time n plus 1 is equal to, and this is a scalar. This alpha is a scalar. It's not a vector or a matrix. This is a scalar. So the state at time n plus 1 is equal to some number times what the state was at time n plus noise. And that value of alpha is usually chosen as a value between 0 and 1. Not including those extremes. If alpha was 0, this would just be a white noise process, and you'd basically say I have no information about how the state changes over time. If this was 1, it becomes a random walk process, and I'll say more about all this again later. So if you're not catching all this, I'll come back to it and say a lot more. But since this came up in this example, I wanted to spend a little bit of time explaining it. Most common, alpha takes a value close to 1, but less than 1, like 0.99, 0.98, 0.999 are common values. And when you pick a value of alpha that's close to 1, but a little bit less, basically what that says about the process model is that your state is changing slowly over time. X of n plus 1 is equal to more or less what the state was at time x of n plus some noise. And if the variance of the noise is fairly small, then the state at time n plus 1 is going to be very close to what the state was. The reason that alpha is a little bit less than 1 is that makes this stable. That keeps it bounded. If it's a random walk and you set alpha equal to 1, then the variance of this process grows over time, and it will grow without bound. And that makes it harder to work with examples. You can still track it, you can still use it, but it's a little bit harder to work with. So often it's made a little bit less than 1, which means that after this goes through its initial transient startup, it approaches a stationary first-order autoregressive process that has a number of nice properties. But the main idea here is that the closer you make alpha to 1, the more memory this has, the more slowly the state changes over time. So the information you have about whatever it is you're trying to track, maybe the frequency, for example, of the waves in your example, Fu, or the rate at which a submarine or a whale, maybe, Scott, if you're working on that, if you've got a whale going through the ocean and you're tracking the whale, that whale's got an awful lot of mass, probably, if it's a healthy whale, and it can't change very quickly. So if you're tracking the dynamics of the whale, you could say, well, if you're tracking the velocity, say the velocity isn't going to change very quickly over time. This is a common way to encapsulate that information, that the state can't change rapidly from one time sample to the next. So we're finally starting to see a way in which you can take prior knowledge about dynamics, about basically inertia, in the broadest definition, and the idea that the state can't change rapidly over time. It can change, but not rapidly. And the closer alpha is to 1, and the smaller the variance on this process noise, the more slowly you're saying that the state changes over time. So this is one of the ways that we bring prior knowledge to bear and represent that mathematically. This is part of the engineering that you're going to be responsible for when you're working with these state space methods. So I'll say much more about that a little bit later when we talk about various ways of representing that knowledge, but that's a very common one, so I want to spend some time on it now. Yes, Scott?
Depends on how far apart your time steps are. Like if you had very large time steps, that it could change a lot in between.
Yeah,
Equals
and
0 and then equals 1, then you need a smaller smaller alpha or larger alpha?
Yes, you're absolutely right. If you really have a continuous time process and you've sampled it with an A to D converter at a constant sample rate, and that's how you got it into discrete time, then you're absolutely right. If you're going to consider various sample rates, then it turns out the amount of process noise you're going to want to scale depending on what your sampling interval is. And I'll talk about exactly how to do that mathematically a little bit later in the term, but your intuition is absolutely right. It turns out that if what you're representing is the, I'll say more about it later because there's a lot of complexities in trying to talk about a continuous time autoregressive process. Then in continuous time things get much more complicated. But your intuition is absolutely right. So we've got our state space model. I'm giving it to you. And in this case, one way of conveying a description of what this represents is to say, oh, we're taking measurements where the measurements are related to the state, where the state is an angle, and we're getting a sinusoid of that angle is what we're able to measure. But we're only able to measure it with some noise. We can't measure it perfectly. There's this additive measurement noise. But the state that we're trying to track is an angle in this case. And I've got prior knowledge that angle, I don't know what it is, but I know on average it's 0. And because the expected value of x of n is 0 if alpha is less than 1. So I know its expected value is 0, and I know it changes slowly over time. That's essentially what this model conveys. And so we have it. We need our probabilities. We've talked about how to do that now a number of times. So all of you at this point should be able to take the process model and quickly arrive at the distribution of the prior. And likewise, all of you should be able to take the measurement model and quickly arrive at the likelihood function. We need both of those in order to do this kind of tracking of the posterior that we're interested in. It was essentially what we were talking about on the previous slide. So we have those two probabilities. They come directly from the state space model. And again, whenever you've got additive noise, this is actually a trivial step, as long as you know what the distribution is of your noise, which you need to. Any questions so far? You guys following? Okay, so for the example that I'm going to work through, there are decisions I have to make. Some of these are model design issues. And normally you'd need to justify this based on your application. You'd need to characterize things or explain how the prior knowledge relates to these. But for now, I chose some values for the sake of illustrating some ideas. So I said alpha equal to 0.99. I assumed the measurement noise standard deviation was 0.4. I used process noise standard deviation that was also 0.4. For the homework, I ask you to go a little bit beyond what I'm going to show you here and consider cases where you have a few different measurement noise standard deviations and a few different process noise standard deviations, so you can see what happens when those change. And you should think about what you expect to happen before you apply that. It's going to be really interesting to see the presentations next Thursday. You also have to specify the initial state distribution, and I'm assuming its mean has a mean of 0, a standard deviation of 0.4, and I modeled it as being a normal distribution. So the whole thing was initialized with a prior at time 0 of being normally distributed with, again, a standard deviation of 0.4. It's kind of consistent throughout. I only did this for 500 samples. This goes from time 0 to time 499. Remember, we have to do definite integrals. And knowing a little bit about this process, I knew the state was very improbable that the state would wander all the way up to 10 or down to -10. And so that was a very safe range to choose for the range of integration. And you can do this iteratively, try a range, guessing where the state is, and see if there's any mass up there at 10 or -10, and if there is, just widen your range. But there are other ways that you could arrive at that same information. So I chose that as the range of integration. And I chose 400 bins or 400 regions to do the integration over, and I chose that because that was ample. The features of the PDF, if you look at how rapidly the posterior fluctuates, I had plenty of resolution in picking 400 regions over this range.
So that range there, we can do that per n, right? We can update that per n, right?
You could. I mean, most people wouldn't, but yeah, you could certainly change your representation and how many regions you have. You could change that over time if.
Because like if my prior is a Gaussian, I can just go out like 5 sigma as like a confidence interval and say my range of integration is my confidence intervals.
Yeah, there would be nothing wrong with doing that. It does add complexity, obviously, but aside from that, you can certainly do that. You're on sound footing mathematically if you're changing the range from one time step to the next, or even changing the number of regions. The representation of the posterior could change over time also if you wanted to. But very few people do that just because it's a lot easier to code in when it's fixed. That's all. Any questions? So I want to make a distinction. The first two bullets, this one and this one, are further descriptions of the state space model. These two equations alone are not sufficient to describe the state space model. I also need to describe the noise processes, both the process noise and the measurement noise, which I've done here. I had a single parameter that needed to be specified, and I had to state what the initial state distribution was. So these first two bullets are really completing the description of the state space model, which you'll need regardless of which algorithm you're using. The bottom three decisions, well, this one, I mean, normally you'd have to run the simulation for some period of time, but the bottom two bullets are parameters of the tracking algorithm, which is distinct from the state space model. The justification for choosing these values should come from characterizing your process, or from the types of measurements that you've taken, or from the prior knowledge you have. Whereas these parameters of the algorithm are usually more related to computation, the trade-off between computation and accuracy. And often when you're specifying these parameters, when we talk about particle filters, a big parameter will be how many particles did you use? And it really comes down to how many particles could you afford to use, knowing that you started the homework at noon and it's due at 4:40, and you've only got so much computation available. So it's really the computational limits that you usually run into. Another reason for choosing 400 regions, another way that I could have justified that design decision, is that I'm going to be displaying the PDF as a pseudocolored image, and this projector is pretty poor quality. And if I had used more than 400 regions, then you're basically talking about 400 pixels, and that projector can't do much more than 400 pixels. So I would be computing something that I couldn't actually display, that you couldn't see. And that might be another reason how you could justify the number of regions. This is a little bit shy. I don't know how many horizontal lines this projector can actually show, but again, it's not even using the full screen. So those are other considerations. Those are other ways that you could reason through how to pick these values of the tracking algorithm. But that thinking, that providing a strong rationale for your design decisions is something I'm going to be looking for in both your homework and in the project. That's one of the things I want you to leave with is recognizing that whenever you're making a design decision, you should have a good reason for it. You should be prepared to defend any of those design decisions that you make. All right. Again, everything that we're interested in, whether you're doing a median, a mode, whatever, comes from the marginal posterior. That's what we're really interested in. And we can certainly plot this at any given point in time. It's just a PDF. But like the pseudocolored image that Fu showed us in his homework, I think it's more informative to look at how this posterior changes over time, and not just look at it at one point in time, but also look at how it's changing over time. And so you'll see in a lot of my slides, I use these pseudocolored images where I'm using the color to represent the value of the posterior PDF. On the horizontal axis, I'm going to plot time. I know people that are used to spectrograms, sometimes you have time on the vertical axis, but throughout this class, whenever I plot this, I'm always going to have time on the horizontal axis. And then the vertical axis is the state. Now note, this only works in the one-dimensional case. I always get the question from students, well, I want to do what you showed us because it's really cool. I want to look at that. But if you're looking at a 2 or 3 or 4 dimensional state vector, you're kind of stuck. I mean, you could plot the marginal for just those and plot them separately, but it's a little bit different. You really have to think that through, because then this suddenly becomes a joint probability where the independent variable, the state, can take on any value as part of a vector. So don't be surprised when you get to working with multi-dimensional states that this starts to become impractical and you can't do it so well. You get a lot of insights from studying this, so I'm going to spend quite a bit of time talking about this example and what it illustrates, as long as I'm not running out of time. Siri there, if Siri done that. So for those of you that are watching the screencast, we had a technical glitch, and I'm sorry, you missed part of the slide. The bottom line is that this is the measurement, this is the actual state that we're trying to estimate, and with real signals, you'll only ever have your measurements. You won't know what the true state is. It's only when you're doing synthetic data generated from a mathematical model of your process where you can see what the real state is. And it's a really good idea. Even those of you working with real data, you're going to have to create a state space model. You're going to have to design one. And it would be a good idea to take that state space model and generate synthetic data where you've got the state, and then compare how well does your tracker track the synthetic data, the true state of the synthetic data. That may give you a good idea of how well it tracks with the real data. So I really want to get to kind of the main point, which is this slide here. This is there are so many cool ideas that are illustrated by this. And I'm sorry that this is, those of you that are here in the class, this is getting washed out a bit by the lighting we have in the room and by the kind of poor quality of the projector. I'm showing an awful lot here. Let me start by orienting you. This, even though it got messed up a little bit somehow, this is the state shown on the vertical axis. And I said I integrated from -10 to +10, but I limited the display from -6 to 6. So this is the state. This is time. I said I went out to 500 samples, but I'm just showing the plot for 200 of those samples. So it looks like this goes out to 199. I'm using a grayscale to represent the posterior PDF. So the marginal posterior PDF at a given particular time is shown by the darkness of the image underlying the colors. So if we look at roughly time 20, you can see there's a lot of kind of blackish color in here and in here. So that tells us that the posterior had two different modes at that particular time. And there wasn't much probability in here or up here. I know that's pink, but it's a transparent pink. And likewise down here, actually there's another mode down here that's rather faint. But down here as well, there was very little probability there. So we're looking top down on how the posterior changes over time. This being a PDF, it's very, and being able to represent it essentially as a histogram, it's very easy to calculate a 95% confidence interval. And I've done that throughout, where we can say with 95% confidence, the state will be within the 95% confidence interval. And I did that by showing the 2.5 percentile by the pink region going all the way up until we get to the 2.5 percentile of the distribution. So it's shown red here, and this is technically a red, but I made it transparent, and that made it look pink. So that's why the colors don't quite match. But that's what this pink region is showing, is from -infinity all the way up to the 2.5 percentile of the distribution. And likewise, you can go all the way from +infinity down to the 97.5th percentile of the distribution. And that's what the upper pink region is showing. So anything that is not within the pink shaded region is within a 95% confidence interval. Pretty cool, huh? I mean, in most signal processing classes, people are not going to be able to talk about confidence intervals because you just don't have enough information to be able to estimate those. But in this particular example, and in a lot of the state space methods, you can actually do it. We have not just a standard deviation, but we've got an actual confidence interval that we can compute as accurately as we've got cycles to compute it. This is optimal tracking, so what we're looking at is the true posterior. It's the only algorithm that will give us a true posterior. Everything else pretty much gives us merely an estimate. So I really like this example also because it's multimodal. Over time, you have modes that sometimes come together, and you have modes that split apart, and sometimes sort of new modes get created where you're basically getting to the limit of the sinusoid, sort of the peak of the sinusoid, and then it continues, and you can't tell if the angle increased or decreased, because when you take the cosine, it's indistinguishable between those two. That's essentially what creates these modes. But we've got a multimodal posterior, and this is conceptually really important because this happens in a lot of applications, and yet a lot of really good, smart engineers will often track this, assuming that they're working with a single mode. They'll apply a Kalman filter or an incentive Kalman filter or some technique like that, and they'll get an estimate, but it's based on erroneous assumptions that the posterior they're trying to track is unimodal. You can see a very simple example. There's only one nonlinearity, that sinusoid, created something that has a lot of modes, not even just two modes, but as we go out and the state wanders away from what its initial value is, we can have half a dozen modes that are significant there. And when you're thinking about tracking, you should be worried about this. It's hard to see, except in the one-dimensional case, where you've got a multimodal posterior, but it comes up more often than you would think. And if it's multimodal, you should be very worried about any tracking algorithm that assumes it's unimodal. Eric earlier was also saying, well, if it's symmetric, surely you would use the mean. And we have, the posterior is roughly symmetric in this time range, around 20 to 30 or so. But you can see the mean of the distribution is in a very improbable location. It's nowhere near where the real state is. It's not near the mode. It's not near the median. It's in this case, in a multimodal posterior, often the mean isn't so good. In fact, if you look at it, the mean kind of stays constant. The mean, it tracks initially a little bit, and then it just kind of stays at zero and stays at zero throughout. Mean is probably not a good choice in this particular, whatever the application is that's driving this. It's unlikely that the mean is going to be valuable. It's probably not what you want to use. Another neat thing, I don't want to run too much over, but another really cool thing about this is if you look at the true state, it's way up here. It's far away from the estimates. And none of you have said it, but you may be like, what are you doing to us? The state is up here, and you're telling us this is an optimal tracker and that these are good estimates of the state? And I'm telling you that it is, because in this class, you should be thinking about the ensemble. And if you think about all the possible values that the state could have taken on and how probable it is that the state would be in various places, what happened here was improbable. The true state in this particular realization happened to be up here. But if I had many more realizations with exactly the same set of measurements, exactly the same data driving the tracking algorithm, you'd generate the same posterior. And most of the time, the true state would be down here, or maybe in this mode. It would be in one of those other modes. What happened here was improbable, but we're not, in most applications, we're not actually trying conceptually to track the real state. We're trying to track where the state is probable, what the probable state is. We're trying to be right on average across the ensemble. We're not trying to be right for that particular realization. And this nicely illustrates that very important idea. We're wrong. It doesn't matter whether you're using the mean, the mode, the median, or some other measure. Pretty much whatever you pick from this posterior, which gives us all the information we could have from the measurements, it would be very, you'd have to be very lucky to come up with some estimate where you're like, oh, it ended up being up here, because that's an improbable thing that the state actually took on for the measurement data that we have available. The evidence didn't support very well where the state actually was. Although you can see it actually ended up coming back down, and then the median and the mode were tracking it quite well down there. So I know that's a lot of ideas. I was eager to cover those key ideas in today's lecture. It's a lot of good stuff that I'd like you to think carefully about. These are pretty central ideas for the whole course, and I'll go over them again on Tuesday when we meet next. I think we're out of time for today, so we'll stop there today.